Thanks. Everyone hear me okay? Yeah, well, I'm nodding heads, that's cool. Okay, I want to talk today about LoRa. It's a radio protocol that's actually taken a lot of interest and a lot of investment recently. So I wanted to just talk about a little bit, just to introduce it to you, and also just to understand it from a security point of view. So if you were to run into it or consider it, what you need to actually think about. So first of all, just obviously you need to explain what on earth this is, talk a little bit about the security features of it, and then actually try and look at, okay, if we understand the security features, how do we attack this system, or, how do we build a system that can withstand attack? Introductions to myself first. I've been with MWR since 2011. You've probably seen me here a couple of years ago. I've done a lot of work on Android, so it's awesome to be sort of moving on and talking about something new. I run our company's operational technology practice, where we're looking at embedded systems, industrial systems, and radio technology. Another quick pro tip, if you're considering starting a research project, make sure there's a hilarious talk title you can get from it. LoRa the Explorer was the obvious choice, but it can be really, really difficult when you've got a presentation and you can't come up with a title for it, so best do the other way. So back in 2015, in the autumn, we decided to go to a conference that's not a security conference. We tried to sort of branch out, and we went to a utilities conference, and this was European Utility Week. This is massive. This is kind of like an InfoSec for the utilities area. So everyone from Siemens right through to small sort of Chinese startups selling sort of smart metering and things like that. Everything in this space, all the new technologies, and we were there to just talk to people to understand, okay, what new kit are you bringing up? What new protocols are you using? And we had to obviously brush up on the kind of protocols we expected them to use. So we kind of had these kind of assumptions. Okay, well, we're going to go to this conference, so let's make sure we really understand Zigbee security, that, okay, if they're using VTLE, that we totally get that. So we got there, and on the first day, we actually found, I think, maybe 2 vendors using any of those. All the others were using completely different radio technology. Which was quite awkward, but also really exciting. So the first evening we went back to our rooms and just sort of reading as much as we can so we could have a conversation with them the next day. So why has this happened? Have we not already kind of solved radio? Are there not already protocols out there? Why have everyone now jumped, in this sector at least, to different ones? And you can break it down fairly quickly like this. So if we have sort of the range of the protocol at the bottom, the power usage at the top. Okay, if we want to send things long range, if we need this to work over kilometers, okay, we'll probably use a cellular network. We'll probably maybe need to use satellite if it's, there's no cell towers nearby. If we're a little bit closer to home and we maybe want to improve the bandwidth a bit, okay, great. We have Wi-Fi, we have Bluetooth, very established technologies, nice and easy. More recently, we've seen this area solved. And this is, okay, what about sort of personal range, or sort of within a small building that's very, very low power? So this kind of home automation side of things, that now you don't need to trail power cables all through your house because, it's all wireless. This thing runs on a battery for years, which is great. The gap is obviously here. And for utilities, for transport, this is a really exciting area if you could solve it. Could you come up with a radio protocol that works over many, many kilometers, but doesn't have the sort of drawback of needing a lot of power, constantly going out to replace batteries, needing some kind of mains connection? It just doesn't work all the time. And this is LPWAN. So LPWAN is low power wide area network. This is sort of the sort of brand name given to a whole bunch of technologies that essentially have these features, that the battery life, and it is extreme battery life, should be able to run on a AAA battery for 10 years. That's at least for the end nodes. Range has to be, we're talking across cities, across, whole wide areas. Bitrate we're not actually worried about. We'll sacrifice that. We're only going to be sending metrics, small information, small commands. So we're not worried about bandwidth. This has become possible using one of several modulations, which I'll go into in a sec. The other factor is it must be cheap. That these chips, these transceivers, these whole devices we're going to build, we're probably going to want hundreds of them. The kind of typical solutions we'll go through in a second need these remote nodes to just be across a city. And if one gets run over by a car, who cares? That's just a few pounds. If it, so you can imagine it gets very, very expensive very quickly otherwise. And I mentioned a couple of areas already. Smart city, if you can actually measure pressure on the water pipes, if you can get any sort of critical infrastructure that you don't want to run cables across, that you don't want to plug into your network, well, now you could just have a node that just reports back metrics to you. I live in Reading. One area that LoRa is already being used for is to measure river flood levels. So these things are distributed around the river. When they sort of obviously measure that the water level's up to a certain limit, they then report back. Actually, logistics is another one that's kind of interesting. I didn't think of until I was talking to people in the area. But there's a lot. Imagine if you've got like the containers, like reefers, so they're actually refrigerated units. And they're being carried on a ship, they're a truck, they're across the city, but you actually want to know what the temperature is. Well, either you're going to have a lot of power draw, or you can just have these small devices now that are using LPWAN. So there's a few modulation technologies. It's pretty much at the moment between ultra-narrowband, UNB, and LoRa. LoRa is actually a spread spectrum, so ultra-wide, and then you have ultra-narrow. They're sort of the two competing modulations. Narrowband is just coming in, and we'll have a look at sort of who's investing in what in just a second. But the idea of narrowband is, could we use existing cellular infrastructure to offer this kind of LPWAN solution? A little bit more theoretical, not as mature as the top and the bottom one there. We're looking at companies. Weightless is a UK company, ultra-narrowband. Sigfox is pretty much the sort of big player in ultra-narrowband. There's a couple of others that are using it as well. Cellular, it comes across as a whole bunch of different names. So narrowband LTE, narrowband IoT. Companies like Huawei are getting super invested in this. Great idea. We can offer IoT solutions using our existing infrastructure. Great. LoRa is pretty much solely owned by the LoRa Alliance. They're the organization that are really, really pushing this. Link Labs are also doing something using similar modulation. So we have, at the moment, this kind of situation of this VHS versus Betamax kind of thing. The big two players are LoRa with LoRaWAN and Sigfox. They are the ones that are grabbing all the headlines, getting huge amounts of investment. But ultimately, if one of them was to become the mature one, then everyone would just jump to that, and the other one might die off. So the big difference with Sigfox is Sigfox build you the network. They have a build it and they will come kind of idea that they will go to, say, London, install all the sort of cell towers or the equivalent for Sigfox, have all the back end all done, and then just offer you, the customer, the ability to buy a node, buy a license, and access web services. So you kind of access either end of it. Great, because now you don't need to worry about installing all that middle kit. They do it all for you. Big argument against it, though, is what happens if they go out of business tomorrow? Well, all my kit's going to stop working. So they got to worry about that. LoRa is the kind of a bit more open source. I'll use that phrase carefully. The LoRa modulation, like the PHY layer, is actually licensed by Semtech, but the layer above it, loads of companies are doing this kind of middle, kind of the cell towers, the servers, and the services. So it's a bit more, you kind of own that, but obviously you need to make the investment. Big players in the area, you can kind of see how it's a little bit split up, but a lot of companies are announcing they are siding with one or the other. In terms of semiconductor manufacturers, also the telcos are super interested in this because it could offer a whole new service. You've already got all this networking infrastructure. How about you can now offer an IoT service on top of it? So a lot of companies are either kind of signing up as alliance members or actually investing. Orange, weirdly, if you see, they're actually doing both. They invested something like 60 million euros into LoRaWAN to install it in several cities in France. But they've publicly said, we're only doing this until our NB-IoT gets off the ground. So there's a lot of companies kind of hedging their bet. Generally, LoRaWAN, apart from ESCO Telecom, is very European-based. Cellular NB is kind of pushed by the Americans, and Sigfox is also Europe, but spreading through to Asia. So that's the idea of this kind of LPWAN. So why choose LoRa? There's a whole bunch here. Why not go look at Sigfox? or one of the NB-IoTs? Well, there's a few advantages. First of all, LoRaWAN, the Mac layer and the app layer, are open source. Anyone can go on their website today. I think you have to type in your email address, but then you can download the full specification. So for a research point of view, that's awesome. It's not a theoretical thing. It's had a huge amount of investment in a lot of cities in Europe, including London. So it's not just a theoretical thing. There's actually sort of value in helping people at this stage. Also, it's not just turning off your lights. And I've seen talks on that before, and it's great, turn off your lights. That's mildly annoying. LoRa has already been talked about being used for actually quite safety critical things. So there's already been a paper produced of how you would use this to automate railway level crossings. And I've looked at one system that was being demoed at the European Utilities Conference that was a burglar alarm based on this. And also a lot of people saying this is great, you can put this into your national infrastructure, critical infrastructure, and you don't have to run wires. Isn't that brilliant? Well, yes, potentially yes, but we need to know about the security of it. So walking around the conference, obviously you start trying to dig, but just like going to InfoSec, you can't really talk tech to the people on the stands normally because it's mostly sales stuff. So when I was asking about it, it's like, oh, Laura, this is great. What's the security? Oh, yeah, it's fully secured. How does it do that? Oh, it uses AES 128. Right. Yeah, okay. So I started going to them and saying, okay, apart from using AES 128, how does the security work? And just the stunned look that obviously stolen their only tagline they were using. So at the moment, there's nothing really out there. And as I say, you can just download the spec, but that's pretty heavy going if you just need to be able to advise someone within 5 minutes if it's good or not. As a consultant, I kind of have to also expect this kind of questioning. I'm going to have someone ask me, we want to use it for X. Is that fine? Would it work? Is it safe? Or alternatively, we're going to use two gateways we want to use. Which one should we use? Due diligence, if we want to look at the security of these products, which one's better? So this is the presentation on the research from sort of October till now, to say the following, to say whether it's even possible to use it securely, to find out if you are going to use it, what's your key controls, and then to actually try and say, okay, here's a white paper with a list of tests in it that you can actually go and use to look at a system. So that's how we work. We looked at the specification, had a look at anyone who's actually released this stuff yet, see how they've done it, produce a paper, and then actually see if we actually need to produce any tools to be able to test it properly. And that's what we've done. So I keep using the word LoRa and LoRaWAN. LoRa is the PHY layer, that's just the modulation. Proprietary, licensed by Semtech. Semtech will license it out. LoRaWAN is the bit I'm actually more interested in at this point. This is the layer with the security on it. This is sort of the Mac layer and above. And that's an open standard, so we can tear that one apart. Okay, let's say we actually want to build a LoRa system now. We've sort of talked about these various components. There's only going to be 3, according to the specification. You have nodes, you have gateways, you have network servers. Nodes are these small devices. I've got one here. Unfortunately, it's all cabled up. Very, very cheap. This one's made by Microchip. These end nodes are going to be the things that you distribute around. They're going to be things with sort of real-world I/O kind of control. They're going to be monitoring stuff. They're going to be taking commands and maybe, flipping servers, whatever. They report back to the gateways. This is an example gateway. And they're going to be using LoRaWAN to actually transmit messages back and forth to the gateways. Gateways, there's going to be far fewer of them. They're going to be powered. And they're going to then report back to the network server. The network server is your typical IT infrastructure at this point. Some kind of interface that the gateway can talk to. How you want to design that entirely up to you. What you then may have is, if you're like licensing this out as a service, is you can say, okay, company X, you can have these nodes, and you can build your own application server. And I'll know to pass all that data through to you, and you can control them. So this connection, entirely up to you, could be using cellular networks, you could run cables, anything you want, doesn't really matter. Obviously, it needs to be fairly high bandwidth. And then the connection between the gateway and the node, that's what's using LoRa and LoRaWAN to communicate. It works on a call-reply basis. So traditional, the Class A setup is that the nodes will, depending on how you program them, send a message back to your application server. You know, the temperature is currently 20 degrees. The application server then has the opportunity to reply. Okay, it's 20 degrees, open the valve. That kind of message. To understand how good the gateways are, this is a map of München. The red pins are gateways. The green area is the area that you could put a node in and it would make it back to the network server. So they've covered most of a city using just 6 gateways. So it's pretty effective. As you can tell, we sort of move into this deeper, heavier area built up. The range drops quite a lot. Obviously out in the countryside a little bit more, much easier. So that's how it works. There's only these 3 components. Only 2 of them are actually talking LoRa, LoRaWAN. So what does a spec actually say about security? And imagine you were given this, right? Your pen tester hat on. So someone says, we've finished. We've built this. It's got 1,000 nodes, 10 gateways. We've already built all the networks, application servers, third parties can connect in. We've built all the infrastructure in the meantime. The attack vectors on this are kind of mind-boggling. I mean, this is a huge, huge project. You could go after the radio, you could go after the devices, you could go after the servers, any internet-facing areas. What would be the effect of a denial of service attack? There's quite a lot. So we wanted to break it down a little bit. The way encryption works, this whole AES-128, this is the way it works. It's using symmetric encryption. So every node has its own unique keys, should have its own unique keys according to the spec. It'll have 2 of them. It will have an application session key, network session key. Application session key is highlighted in red, network session key is highlighted in blue. Now what would happen is the node encrypts using the application session key and then signs, makes the message integrity check using the network session key. Goes through the gateway. Gateway is completely blind. It has no ability to decrypt message. It's got no access to keys. It just dumbly forwards everything on that it sees that is a legitimate LoRa packet. The network server can then, it's only got the network key, so it can check. Yes, that's an official message. Yes, it had the right key. Pass it on. I know which application server to send it to for the other fields, telling me which one to send it to. The idea being, it doesn't matter if the network server is owned by a telco, only you can then decrypt it. That's the idea. Of course, there's other issues of what if there are 2 like LoRa solutions in the same area. You can actually shift the channel slightly, although it shouldn't affect it too much. And these are command messages. Command messages are only sent by the network server. The network server only has one of the keys, so it's going to use the key for both encryption and signing. So this would be a reply, this time sent by the network server to say, could you actually shift to channel X? Interesting, where it starts getting a little bit more grey around the specification is how exactly do you join a new node to the network? You don't just want me, a terrible person, connecting into your LoRaWAN system. You only want your official ones connecting when you want them to. So joining, you have 2 options. One, you could just program the keys when you're manufacturing them. Put them into the nodes, throw the nodes out into the field, they start working, they've got the keys immediately, so they can just start talking, that's fine. The other one is more complicated, is where you just still put a key onto the device, but it doesn't have the session key set up yet. So what you need is some kind of exchange when the node starts up, using the one key it does have to establish the 2 other keys. So we have our node, it has a unique application key on it, again, AES-128. So, and this is, the node's going to send this to start off with, and this is our evil person in the middle trying to listen in, working out what the keys are. So the node is going to send a join request. It's going to send, okay, I belong to this application, I am this device number, I've created a random number, and I've signed it with my app key, not encrypted, just signed. So okay, he can get those, that's fine. So AES-128 HMAC to sign those. The server then needs to generate another nonce, and using those values, it calculates what the application session key, the network session key should be. it should also, and this is where the specification doesn't really talk about it much, it should also check that that node should even be joining or sending that message at this point. So that's the kind of consideration we need to start adding. These are the formulas used. Again, this is all in the specification. So the server's going to work it out this way. It's going to take the app key, which it also knows, take the nonce, the other nonce it's just produced, and actually produce the two keys. It will then send, yes, you can join, and it's going to send its app nonce back, but this time actually encrypt it with the application key and signer. So now both sides have the information, and man in the middle is completely stuck without that. So we can now join networks safely to our network, which is great. How about the messaging itself? We're going to, as I said in the diagram, it's going to be using the application session key and the network session key. For application messages, encrypt with the app, sign with the network. The network messages, we can only use the one key, but that's fine. Okay, let's get a bit mathy. It's actually using AES in counter mode, which means it's going to be producing a key stream. That key stream is then getting XORed with our message, and that then gets sent across. The idea is that the server can produce the same key stream because it has the same information, XOR it, and get the data out again. A key point of this is obviously you don't want to produce the same key stream twice, quite dangerous. So what it's going to use is these counter values. The idea being that when a node starts, it's on 0. Every message it sends, it's going to be incrementing its counter. And then on the server side, the server can do the same. Okay, I've received one from that node, increase that node's counter. So it can always produce the same key stream as the node, but it should never produce the same key stream twice. The XOR message goes into there, so that FRM payload is our data, the metric, it's 20 degrees, whatever. That gets encrypted. We then sign it with the message integrity check using the network key. So that's pretty simple. We can add nodes, these nodes can message us, we can check the signing, we can check, has it been tampered with, we can decrypt it. Great. Class B is to what they've done when, obviously, some of their customers have put their hand up and say, that's not going to work for us. What if our nodes are inside containers that are constantly moving around the city? What if they're in a car or something like that? How does the server know to send a message to that particular gateway to know that it's going to reach that node if the node's now moved on? Well, okay, so LoRaWAN added Class B systems. Similarly, you'll have times where the network needs to message you, where you want to contact the node first. You don't just want to wait and reply. So that's what this solves. Gateways at this point suddenly become active. They suddenly start doing stuff. They're going to start sending out messages to say, hey, I'm gateway number 3, this is my GPS coordinates, and the time is currently this. The node that way can then receive all of those messages which are sent synchronously and pick which gateway is the closest. If that one has now changed, it will send a message to the server, and the server can say, okay, it came from that gateway this time. Right, I know to talk through that gateway to talk to it. So useful to update. The time it's then received in the node now says, okay, I'm now synchronized with the time sent from that gateway message. I now know at X seconds I should listen. And because you only have these short listening windows, you can sleep for a lot of the time, and obviously far more efficient for battery life. It also allows multicast messages. So now you can send one message to all the devices, because they're all going to be listening at the same time. So all of that, that's all sort of the technical side of it. Is it actually secure? You can imagine these systems are going to be far more complex than that. You can have engineers pulling stuff out. Oh, this one broke. This one's terrible. The latency, let's redirect everything. Oh, the network server's fallen over. It's going to be incredibly complex. So how do we test it? Let's break it down. So messages, there's some things we can do very, very quick. First of all, obviously check signing before encryption. This is the kind of stuff that's in the spec. And to have an official LoRa Alliance device, you must have passed their tests, but ultimately it's probably on you, depending on your role, to develop this and implement it securely. So if we don't check the signing before the encryption, there are several attacks we can do. If we're not incrementing our counters properly, then we're producing the same key stream. That can be dangerous. If we're sharing keys around, and yeah, again, a lot please don't do this. It's up to you to actually implement that. So what happens if we were to decrypt before we check signing? Well, given that we're XORing out using our key stream, it's possible to start swapping bytes. So if I know the structure of the message as an attacker is roughly that, those bytes here will always be 24 because you're just XORing it. So if I just start flipping bits, then I can start changing these values without knowing what the key was. Obviously, the signature check should just catch that straight away, but that's up to you to implement. F-counter manipulation, so denial of service attacks with these kind of systems is probably going to actually be quite expensive. You can imagine the kind of CryptoLocker attack is also. The big point is with counters is they should always increment. If you get one lower, then that's out of sync or, it's rubbish, discard it. So if we were to be able to send a message with the counter set to the maximum value, you've just bricked that node. That node will just be ignored from then on, so pretty dangerous. Obviously, check the MIC first. If you're replaying using the same key stream, then you have the opportunity to XOR stuff out because you've got the same key stream being XORed. Therefore, if you XOR two encrypted messages and you know the plain text of one, you can get the plain text of the other. Duplicate keys is pretty obvious. There's big messages to say, please don't use them, but it's up to you. Or again, guessable keys. If you're basing it off, the MAC address or something equivalent, then it's possible to start just sending your own messages as an attacker. MAC-only messages. These are the network messages. Change channel, do this, do that. Only uses one of the keys. So again, we actually, if we do get that one key, then we're in and can actually do quite a lot of damage. The commands you can actually send, to mention some of these, you can get the status, you can change data rate, transmit power channel, or proprietary. Potentially these messages are less secure, you're only using one key now, and there's a lot you could actually do to damage a system. Now that's really interesting because some companies clearly don't get the fact that network keys by themselves are sensitive. They've obviously assumed, well, yeah, but you've got an app session key and I don't know it, so it's fine. So the Things Network is a hobbyist thing, so totally fine they're doing this. This is in London as well. But for the hobbyist community, you need to know the network session key that the network's going to use. So that's on their website. So anyone right now could produce something to knock over, brick, any node that's currently on the Things Network in any country. Okay, the over-the-air signing. So when a node joins, we could try and do that as well. We need to worry about whether we could rejoin. If we can send it again, produce new nonces, get new session keys. You leave the actual node out in the dark because it's got the wrong ones and the server will just think it's malicious and ignore it. Similarly, if we're able to guess the keys, we can do a whole bunch of attacks on listening or start spoofing messages. Key management is not talked about at all in the specification, and this is where some of the most interesting attacks are. You've got to have a server that the network server and potentially application servers can access to get those keys, to be able to decrypt and read the messages, but also to send replies. Now, that's potentially a single point of failure and a really critical asset that you want to worry about. Who's got access to that database? What happens if that database was crypto-locked? Your entire IoT network running on LoRa now doesn't work. It's a really, really critical thing that you need to isolate away. The other thing is the device is the nodes themselves, and we've had quite a play with these. I'll show you some of the work we've done on this. But physical attacks on these nodes. These nodes are going to be out in the city. They're in people's homes and their cars. Various interested enthusiasts, will probably pull them apart at some point and try and work out how they work. A LoRa node is probably going to have something like this. The antenna, you're going to have your transceiver that does all the encryption and signing, so that's going to have all the keys in it. Some kind of connection, the one I've got is a UART connection that goes to a microcontroller that then does all the sort of businessy logic that's sort of reading whatever measurement it is that's sort of producing a message, sends it to the LoRaWAN transceiver, and that then gets sent out. So the nodes must have these keys. They should be unique per node, but would be an interesting one to test. This is the transceiver I've got here. So normally your microcontroller would connect into these pins, and then you can actually use this to send stuff. So potentially we can steal the keys from the node. We could also try going after the firmware, because it must be parsing the PHY layer at least, or the microcontroller might be doing parsing on the actual application data that's being sent. So it could be interesting. So could we just pull the keys out? What is this transceiver? What is this magical black box? Well, if we took the shielding off it, you can actually see it's a PIC chip, PIC18LF, that's got debug ports, so we can connect our PIC-kit debugger to it. We can try and actually look, can we pull the keys out? Have they set the registers correctly to stop attackers doing that? Yeah, actually, annoyingly, they have. One interesting thing is you can write to individual code blocks. So these PIC chips let you write to one sector and leave the rest of the code intact. You can, they have made a mistake on the flags to set that one block can read the code from another block. So if anyone's smart enough, and I would be interested to talk to you afterwards about this, can you write code flash to one part of the block with some kind of NOP sled that then reads out the memory from the other sections, and then would throw that one away, get another device, write to another sector, and that way you'd get all 4 sectors of code out. Could be a good way of dumping the firmware. There's nothing in the datasheet to say there's any kind of protection against this or side channel analysis. These devices actually have a way of measuring current draw exactly to that chip. So should be fairly straightforward to do power analysis to work out crypto, unless they're using a secure AES library, maybe. We can go far, far cheaper and dirtier. If the server, the network server and the application server is just expecting data back and then putting it into a database, we have all the classic network attacks. SQL injection. I actually put together a demo that does cross-site scripting through this because these values are just being displayed in the engineer's web app. So if we just replace the microcontroller part, we can just send in anything I want. And the great thing about that is if the transceiver has the keys, it will just start encrypting and signing it for us. Very, very useful. So we need to worry about those. Obviously, internet-facing components are pretty straightforward. Chances are it's going to look like that. That is the implementation for several of these solutions. These gateways are just talking out 3G dongle out over the internet to a web service. That web service, again, single point of failure. What happens if you just DDoSed it? You know, suddenly the nodes wouldn't be able to communicate anymore. It's a pretty big fool. We could start looking at brute force attacks against the MIC, but 4.3 billion messages you'd have to send is probably a little bit extreme. So probably something you'd want is more like a private APN. You can then actually VPN to make sure that only the gateways are going to talk to the web services. Again, you then might need to worry about what's the physical security of these gateways if they have assets like this. Class B is where things really start falling apart a little bit on LoRa security. Essentially, to be able to send a broadcast, you need to share keys. And the LoRa specification just straight up says, like, we don't really know how you're going to do this. We just kind of support that you can. So please, when you're going to send a broadcast, magically change all of your nodes, app keys, and network keys to be the same, because we're going to send the same message to all of them. And then please magically change them back again. So they said they're not allowed to send MAC messages using this, but again, entirely up to you how you've implemented that. So Class B generally is be careful. Multicast messages, yeah, good luck trying to do that securely. It's going to be really, really tricky. Gateway beacons get properly interesting because there is no security on them. Gateway doesn't have any keys. It can't do any signing, can't do any encryption. They're going to be sending their GPS coordinates and a sort of a network time to all of the nodes. So first of all, as an attacker, that's very easy to war drive because you've got the GPS coordinates of all the gateways that potentially have a secure connection back to the server. The other interesting thing is that the nodes are using these values, and I've seen some sort of Stack Overflow type chats about it. Everyone's actually now just setting the node's system time to be the message sent by the gateway. Okay, I've just received a message, it's currently 12 o'clock noon, set the time to that. No encryption or authentication, so I have no idea what would happen if you just start sending, 1st of January 1970 to these things. So, in summary, having read through this, I think it is perfectly possible to build a secure LoRa network. There's a lot of onus on you to put the spec properly, to implement the spec properly. That was obviously ridiculously quick going through this. The spec is pretty big. So what we did was put together a white paper on this. So if you're interested in this, that's freely downloadable from our website. It goes through each of these areas in far more detail, and the test cases in far more detail as well. The last thing I want to do is to say, obviously, we were looking at, if I can do this, producing tools. So one thing I wanted to do was say, well, okay, if you can get gateways are just packet sniffers. We don't have to do any kind of software-defined radios on this because the PHY layer is black box. But what we could do is take a gateway, just have it record every packet it ever sees. And then we can use that to try and inspect to work out what information is being leaked. We could actually maybe test the keys that we've stolen off the device or a server. So hopefully this is all still running. So I've got a gateway here. And what we can do is I'll just send a message from a node. I think this is something like AAAA. So I'm just setting it all up. I'm just going to make it go through ABP. Quickly sign up. And the gateway is going to listen. Now this node I've set to just use a key of all zeros. And that's sent a message. And our nice little web interface in the front end, we can actually now inspect and start parsing this traffic. So okay, it was sent at 10:37. Yeah, it was. So I get all this information, which bandwidth, which port it's going to, so that's to do with the application. I can then look at that encrypted payload as well. And if I know that the key is all zeros in this case, okay, that's just random data on that one. Let's have a look. Okay. So obviously you're going to pick up random messages as well. Interestingly, this is going to be picking up every message, I've just realized, and we're currently in London, so that might have been an actual LoRa system in use. Cool. So we can decrypt this one. Nope, that's someone else's system as well. Live demos, you got to love them. Okay, I can try and send one later on. If you're interested in this kit, I'll have it around for the rest of the day. But it's essentially using a node so we can generate our own messages and sort of hand set all the keys so we can start trying to inject messages into a network. We also have a gateway so we can go war driving or actually try and passively decrypt and read these messages. That's everything I wanted to cover. Does anyone have any questions?